Okay, so this video is just to summarize the chapter 4 about Laplace transform. So this is Laplace, how to use Laplace for solving differential equations. We start with the definition. If I have a function f of t, we can define the Laplace transform. F of s will be the Laplace transform of f of t, which is defined as the integral between 0 and infinity, exponential minus st, f of t dt. Now, using this definition, we have as well that L of f of t is the inverse Laplace transform of f of s. So the Laplace of basic functions will be the following. t power n will obtain factorial n over s power n plus 1. Laplace of exponential at will be 1 over s minus a. Laplace of cosine kt will be s over s squared plus k squared. Laplace of sine kt is k over s squared plus k squared. We have another two, which are Laplace of hyperbolic cosine of kt should be s over s squared minus k squared, and Laplace of hyperbolic sine of kt is k over s squared minus k squared. Okay, so with these functions, these Laplace transform are used as the basic one, and considering the linearity, we can find the place of several functions. Now, the other thing that we need is Laplace of derivatives. For example, if we have a function y of t equal capital Y of s, its Laplace transform. We'll have the following relations: Laplace of y prime t, you can just get it from s ys minus y0, and Laplace of y second t is s squared ys minus s y0 minus y prime 0. So this can be used for solving differential equations. Another thing that we'll need is the translation theorems. The first translation theorem, which is as well called the S-shift theorem, it states that the place of exponential at times a function f of t will be f of s minus a. Means we need to find the Laplace of f and just replace s with s minus a. And of course, we can use it in both ways. That means for finding inverse Laplace transform of translations. The T-shift or second translation theorem is the following: f of t minus a times u of t minus a. The Laplace transform will be Laplace of f of s multiplied with exponential minus a s. Now, what is u of t minus a? Is the unit step function. U of t minus a is defined as 0 when t is between 0 and a, where a is any positive number, and it is 1 when t is greater or equals to a. You can define another function which is v of t minus a, which is 1 minus u of t minus a, is defined as 1 when t is between 0 and a, and it's 0 when t is greater than a. Now, what do we do with this? Let's see an example of differential equation. Let's say we have to find the solution of this differential equation using Laplace transform. Y second minus 4y prime plus 5y equals 0. And we have the following initial conditions. Y of 0 is 3 and y prime of 0 is 13. Now, the first step is to just apply Laplace transform using the linearity. We obtain Laplace of y second minus 4 Laplace of y prime plus 5 Laplace of y, which has to be 0. Laplace of y second is s squared ys minus sy0, that means minus 3s and minus 13, minus 4, we have here sys minus y0, that means minus 3, and then plus 5ys, it has to be 0. So factorize with ys, we obtain s squared minus 4s plus 5 times ys. And then in terms of minus 3s, we bring it in the right side, becomes 3s. We have minus 13, here we obtain plus 12, so it will be minus 1, in the right side becomes 1. Which means ys is 3s plus 1 over s squared minus 4s plus 5. Now, to find the solution of this differential equation, we just need to find the inverse of this Laplace transform. But this is where we have to use the first translation theorem. We have to complete the square here for the denominator, s squared minus 4s plus 5. We write it as s minus 2 squared plus 1. So which means if we use the first translation theorem, the value of a should be 2. Now we take the function as a function of s minus 2, which is now 3s plus 1. And denominator, we write it as s minus 2 squared plus 1. Now, the denominator is already a function of s minus 2, but not yet the numerator. So we just need to change it. We have s, we just replace it with s minus 2 plus 2. And then we use brackets. Plus 1 over s minus 2 squared plus 1. Now this is 3s minus 2, then we have plus 6 plus 1, so plus 7 over s minus 2 squared plus 1. Now this is a function of s minus 2, means to find a function of s, we just have to replace s minus 2 with s. So f of s is 3s plus 7 over s squared plus 1. Now the inverse Laplace of this function, we can just use the linearity. It will be 3 times inverse of s over s squared plus 1. and then plus 7 inverse of 1 over s squared plus 1. So, which is using the table of Laplace transform, we obtain 3 cosine t plus 7 sine t. Now, since we are applying the first translation theorem, at the end we obtain that y of t, which is the inverse of 3s plus 1 over s squared minus 4s plus 5. The formula is exponential at, that means exponential 2t, and then times f of t, which is 3 cosine t plus 7 sine t. Sine t. Okay, so this is the solution of the differential equation to obtain using the first translation theorem. Now, let's see another example. Let's say we have a function g of t, which is a piecewise function. It's -1 when t is between 0 and 2, and it is t when t is greater or equals to 2. Now, our objective is to find Laplace of g of t. Since the function is splitting at 2, that means it will involve the use of u of t minus 2. U of t minus 2, which is by definition 0 between 0 and 2, and it is 1 when t is greater or equals to 2. And the other function that we define, v of t minus 2, which is 1 minus u of t minus 2, is defined as 1 between 0 and 2, and it is 0 when t is greater or equals to 2. Now, we could write g of t as -1 times the function having 1 at the upper side. That means v of 1 t minus 2, and then plus t times u of t minus 2, which is negative v is 1 minus u of t minus 2 plus t times u of t minus 2. And then we obtain -1 plus t plus 1 u of t minus 2. So the Laplace transform of g of t will be negative Laplace of 1 and then plus Laplace of t plus 1 u of t minus 2. And this is where we want to use the second translation theorem. We said if I have f of t minus 2 with u of t minus 2, then I can apply the second translation theorem. Just multiply f of s with exponential minus 2s. So here, what we need to do is just define a function f of t minus 2 to be the function near the u of t minus 2. That means here t plus 1. But if it is a function of t minus 2, we would like to see t minus 2 in the right side. So we just write it as t minus 2 plus 3, which means f of t is t plus 3. It means f of s, if we apply Laplace transform, we obtain 1 over s squared plus 3 over s. But we could write 1 plus 3s over s squared. Now, applying the first translation theorem and combining with the first part, the place of g of t is -1 over s, and then plus exponential minus 2s times f of s, which is 1 plus 3s over s squared. Okay, so this is how to apply the second translation theorem for finding the Laplace of a piecewise function. But here there will be an option. I just say as option 2, you can still find the Laplace of the given function without going for the second translation theorem, because g of t is -1 between 0 and 2, and is t when t is greater or equals to 2. Now, one way of finding the Laplace transform is just to go back to the definition. We have to integrate between 0 and infinity, but we split in two parts. The integral between 0 and 2, exponential minus st. On this interval, f of t, g of t is -1, so we just write -1 dt. And then plus integral between 2 and infinity, exponential minus st times t dt. So by integration by parts, and here integrating this part, we can just find the Laplace transform, and we obtain exactly the same result as for the first method. In other words, if I have a piecewise function, I have two choices. Either I write it in terms of unit step functions, apply the second translation theorem, or I just go back to the definition and integrate with different pieces, depending on how many functions, how many parts I have in the piecewise function.